Okay, recording has started. And Amanda, are you ready?
Is my screen sharing?
I can see your PowerPoint.
Okay, cool.
And are you
Wait a
starting the
second.
slideshow? Yeah, okay.
All right.
Starting. Okay, good. We see the slideshow.
Okay,
Okay, go
cool.
ahead.
So my project is regression modeling event-related potentials, and in particular, we want to look at how contextualized emotion influences language processing. And this is actually a reanalysis. All right, so a little bit of a literature review. So in the past ERP literature, there have been some studies that have looked at the effect of emotion on language processing, and in particular, there is this really cool component called the N400 that a lot of people have looked at. However, in the past literature, the findings about the N400 have been a little bit inconsistent, and so one of the objectives or one of the aims of this project and reanalysis is to kind of like provide a different perspective on the N400 component, and yeah, kind of like solve the mystery. All right, so the current study, a little bit of a quick overview of the experimental design. So the experimental stimuli were sentences, and the sentences they varied in their valence, meaning we would have like emotional sentences, and we would also have like neutral sentences. And also, these sentences would be ended by ending words, and these ending words would also vary in emotionality. So we would have like neutral ending words and also emotional ending words. And then the third manipulation is the plausibility of the sentences. So about like half of the sentences were like plausible sentences, whereas the other half was just like sentences that did not make sense. And aside from those three, manipulations, we also added, not added, but like the original analysis did not like particularly manipulate semantic constraint. And this is a psycholinguistic index, but I don't really have that much time to go into the detail about it. But these sentences they also varied like to a certain extent in semantic constraint, and so eventually we decided to put semantic constraint into our regression model. And below is a snapshot of how these experimental stimuli were presented. All right. So the EEG recording, we had 20 subjects, and EEG signals were recorded at 35 channels, and we had 1,101 time points. And this is something that I find quite interesting, about MATLAB versus Python, which is like initially the analysis was done in MATLAB, where there were only like 1,100 time points. However, when I fed the data back to Python, like there was just like this one additional time point, and I don't know why that is, but it didn't make much of a difference. So yeah, and the online reference was the vertex channel, which means that we would then have to re-reference the signals to conventionally the average of the left and right masked, and the re-referencing was done in MATLAB. All right, so the ordinary least squares regression model. So regression was computed for each subject separately. So we computed regressions for 20 subjects, and here's like the the regression equation. And so we have like four manipulation factors, meaning that we have four main effects. So this gives rise to six two-way interactions, as well as four three-way interactions and one four-way interaction. And so basically, we put everything into the model. All right, and solving OLS equations is fairly easy. It's just like one single line of matrix operation. And initially, because like this is actually the first time I've really used M&E Python, and I wasn't really familiar with it to begin with. And initially, I did not know that M&E had this built-in function for calculating RERPs or for fitting linear regression models to EEG signals. And so the first thing I did was I did everything from scratch. And then until I realized that M&E actually came with this built-in function. So I later went on to kind of like expand this emily.stats.linear regression function, and I kind of made it into like a mini Python Pipit solvable package, which kind of looks like this. All right, so we have a lot of regressions. Like not only are we fitting regression models to 20 subjects, but each subject has like 35 channels times 1101 time points. And so that's a lot of comparisons if we're running the stats. And therefore, we need to correct for a lot of multiple comparisons. And so, like, maybe the most classic way of correcting for multiple comparisons is to do the Bonferroni correction, which is not realistic in this case, but it's way too strict and stringent. And so instead, we did this Benjamin Hochberg control procedure to control for false discovery rates instead. And this is kind of like a mathematical proof that I wrote a while ago, but I'm not going to go into too much detail about it. So basically, we use this false discovery rate control procedure to correct for multiple comparisons. All right, and then the second question is that even though we have adopted like a less strict and less stringent way of correcting for multiple comparisons, we still have a lot of like way too many cells to correct for. And so like after some discussion sessions with Dr. Lee and also Kara Fedemeyer, we eventually decided to kind of like group these cells into spatial temporal ROIs. So we grouped channels together and also averaged the signals across 25 millisecond intervals. And this significantly reduced the number of cells that we needed to correct for. And all right, so now the results. So we found a very widespread effect of sentence valence that was really persistent, starting from 250 milliseconds all the way to 750 milliseconds, almost over the entire head. And also we found that greater implausibility elicited more negative and then more positive responses during the 250 to 500 milliseconds and 600 to 1000 milliseconds time window. And this is really a great reality check because this 250 to 500 and 600 to 1000, these two time windows correspond quite nicely to the typical N400 component time window and the LPC or LPP component time window. And this really does well replicate the past literature where people have found that the N400 amplitude is correlated with sentence plausibility. And aside from those two really significant robust effects, we also found this frontally distributed word emotionality effect. And this is a little bit harder to capture because like the time window 400 to 700 really doesn't fit into either the N400 or the LPP. And the distribution is kind of weird, so we're still trying to come up with a better explanation to explain this word emotionality effect. And also, we did not find any significant effect of semantic constraint or any interactions with semantic constraint, which I think is a little bit weird because I would have expected some sort of an interaction with it. And I think this could be due to because like there's this component called the frontal positivity, which people are saying that could be all or nothing, like the action potential. And so if this is really an all or nothing effect, then the regression model is not really accurate because like an all or nothing relationship is not like strictly a linear relationship. And therefore I'm actually thinking along the lines of fitting a logistic regression model to further probe the semantic constraint effect. So yeah. And here are two graphs that show the results. So like on the left side is kind of like the grand average graph of the regression coefficients. And so if you're familiar with ERB components, you can see that the red line represents the plausibility coefficient. And the red line really, patterns nicely with the typical N400 waveform pattern. And so it's a nice reality check. And also the orange line represents the sentence valence. So you can see that, it starts from 250 all the way to like 750 or the end of the epoch, and it's like persistent positivity. And on the right side is what I call heat maps. So basically, the black regions, the shaded regions, are the regions in which the coefficients are significant. So yeah, these two graphs just kind of summarize the regression results. All right, and so I'm actually really looking forward to summer break because I think there are so many directions in which I can improve on this project, and there's a lot of directions for future work. So the first one is that, even though we adopted the Benjamin Hochberg false discovery rate procedure to control for multiple comparisons, this is not really realistic because in this model, they assume that all the comparisons are independent, which is not really true if you think about which is not really true in the case where your channels are like 3D configured, and there are certain spatial relationships between these channels. And so I'm thinking like MNE actually comes with this permutation based cluster analysis function that attempts to resolve multiple comparison issues. And so I'm thinking I could employ this function to correct for multiple comparisons, but we need to define like an adjacency matrix that tells you which channels are neighboring channels. And I'm really struggling to find like a good way to define the adjacency matrix. And so currently I'm thinking along the lines of graph convolution, but I'm not really familiar with it, so I'm going to have to look into it. And secondly, I did not mention, but like one of the motivations that got us to this reanalysis was that we wanted to look at predictive language processing or pre-activation. Like when we're reading a sentence, we're going to be actively predicting the upcoming word. And we were thinking that perhaps we would predict upcoming emotionality as well. And so if this is true, then we can look at the sentence pre-final words, because currently we're still time locking to the sentence final words. And so we can look at the pre-final words and look at their patterns and do some sort of similarity analysis between the pre-final words and the final words, and see if there's going to be like any interesting findings. So these are my future work directions, and yeah, that's basically it. And thank you guys for listening.
Okay, thanks, Amanda. Really awesome work. And we have no time at all. I think we will have questions pushed directly to the Discord channel. Okay, Amanda?
Okay, I'll take a screenshot of the chat box. Okay, sure.
Yeah, thanks. And so we very quickly, I mean, it's great work. So definitely a lot of questions that we could address later on. I'll move on to the next person who is, who's the next person? Jing-Xiang. Chin-Xiang.
Yes.
Yes,
I
I
hear.
see you. Yes. Please share your screen, Chin-Xiang, and then
So can you
lie
see my
detector.
screen?
Yeah, I see your lie detection Python notebook, right?
Yes.
All right. And now you have your slide. Okay, please start.
Okay. Okay. My project is lie detector. Yeah. So as the project proposal, my original idea is want to use the EEG plus maybe the micro expression or eye tracking to detect the subject is lie or not. So my first problem is how to find people who lie to me and get the data. So after proposal, I try to find some paper. The first one is it's a IEEE paper. It used the CNN model and the EEG signal to learn the people, the subjects lie or not. And another one is a little bit close to my idea. They use the image and use the machine learning try to detect the subject lie or not. And the blood diagram look like this. The up one is the EEG. They use EEG and machine learning to learn these people, this EEG signal is lie or not. And another one, they use the face image, and I use VGG, is a machine learning model to, and some classify like SVN or LDA, and tell this one is lie or not from its face image. So my first step is I have to have data to learn. So I try to get data from this project. This is also an EEG light detect project. They use two channels. Here you can see two channels, and test the subject who is telling lie or telling the truth. And so I get the data from the internet. And okay, I will switch to my to my Colab notebook. So I get this data first and upload to my Google Drive, and then use it as the database. Okay. Unfortunately, it's smooth. So I get 160 data. Half is lie, half is truth. And then I try to build some model to learn this EEG data. So first one, and the EEG data look like this. This is lie EEG spectrum, and another one is the truth. Okay. So I try to use some model to learn this EEG. The first one I try is DML model, and I load in. First, I build a CN model and load in the data set. And after learn, you can see the result is not so good. Just like the random guess, yes. So, but it may be the data is not enough for learning, or another one is my model is not good enough for this data. So I try another one is the LSTM model. LSTM I tried 3 times, and you can see the result here. This is the first one, my first LSTM model. Since like a little bit better than the free than the random guess. It's about 65 or maybe 70% to get a right answer. And this is first one, and the second one. The second one, LSTM model, yeah, better, a little bit better, around 70%. But because the EPA is not so much, and the data is because 160 sample is not very much data for this model. So I thought the result is really good to reach 70% to tell the right answer. So I also tried the third one, LSTM model, and it's almost the same as the first one. It's around the 65% accuracy. So I tried another one is the CNN model. I tried this one because the first paper I found, I just showed in the PowerPoint, they use the CNN model. So I built this model like the paper, like they do in the paper. They use convolution 1D, and also the hyperparameter I said as the standard stand. And we can see the result here. And also the EPAR, they use 200. I use the same EPAR stand they do. they've done before. And we can see actually it's yeah, just like the random guess. It's not a good result. But in that paper, they say they can reach around maybe 80% accuracy. So maybe they use the because of their data set. I didn't use their data set. I used another project's data set. So maybe the data set different, and or maybe some hyperparameter I didn't set as them before. Yeah. So okay, that's the current status I do, and I'll back to my presentation here.
Okay.
Yeah.
Thanks. This is a great application of neural network. Very interesting work. I had a question. So maybe I think maybe your LSTM perform better than CNN and DNN. Is that right?
Okay. So, oh, sorry, my time up. And
yes.
okay, maybe 30 seconds. I say my next step for future. So I may do some further steps. First one is one-time code and maybe normalize my data. Or I also want to try the transformer or the multi-model like this one. So I can use the eye tracking or face image or EEG data, some voice, and use the transformer model to training, and then we can get if it is live or not. Or we can get some other information to reach the text. Okay, that's all.
Okay, yeah, thank you. So I was wondering if you have, I mean, if maybe your LSTM is performing better than the CNN or DNN, right?
Yeah.
It's maybe because you're doing eye movement, right?
Sorry?
Because you are doing eye movement, right? Can you hear me?
I didn't get you.
Can you hear me? You can't hear me? Or if you see the text, because you
type in the
I type in the chat. Can you see the chat?
See the chat. Okay. Yeah. Maybe because LSTM has temporal, yes, can convert with DSS. Yes, I guess that you still not incorporate time. Okay, I get it. Yeah.
So your because the eye movement is one after the other, so the time is important. The timing, the start and end is important. So maybe in future analysis you can think about it, like your models might need to capture time. It's important to link what when people lie or when they don't depend on what was happening before actually. Yeah. It's not a static state, it's a dynamic state.
Yeah. Okay, thank you.
Any other questions? Okay, if not, we have to quickly move on to the next person. And at this point, I will hand off to Prof. Jun-Xian because later on I have to step off. And Jun-Xian, the next person up is supposed to be Ting-Hsin. So I'll hand it off to Jun-Xian. Yeah, I will still be recording the session, so don't worry about the recording. So yeah, just carry on the session as per normal. Yeah.
Okay. Yeah. Has Ting-Hsin online now? I have not see her on the. I do not see her on the list on the list.
Ting-Hsin.
Ting-Hsin, yeah. Okay. Yeah.
I'm seeing her. I'm seeing her screen, not screen, but her face.
Ting-Hsin.
Yeah, she's. I think she's on here.
I think she, yeah, I saw her. Yeah, Ting-Hsin. Ting-Hsin, can you start to share your screen and turn on your mic? Hello, Ting-Hsin.
Anyone hear me?
Anyone? Can you speak louder? Yeah.
Is the sound?
Yeah.
Okay.
Okay. Yeah, we can hear you. Okay. I think then you can start to share your screen and then run the presentation. Yeah.
I need to. Um, um, I'm currently having some technical issue because I switched computer, so my computer now that currently I'm using cannot share my screen, so I will use my laptop. So
Okay.
probably give me
Mhm.
1, 2
Okay.
seconds. Sorry.
Mm. Mhm.
Let me screenshot the things.
Or maybe while we are waiting, is Xuan-Yu and Wei-Hung, are you ready for the presentation?
Okay, so we have so we first to present our
Yeah. I think while we are waiting, we can just switch that you present first, and then after your presentation, Ting-Hsin, then we let Ting-Hsin to present her work. Okay,
sure.
Is that fine with you? Okay.
Okay, sorry, it works. And
Okay, so Ting-Hsin, please take your time. So we will let the Xuan-Yu and Wei-Hung to present first. Then move to Ting-Hsin's presentation.
Okay, sorry
Okay.
about that.
That's okay. Okay.
so can you see on my screen?
Yes. Okay.
Okay. Hello everyone. We are Wei-Hung Lin and Syuan-Yu Lin. We're a master student majoring in psychology from Taiwan Hub, and our project is unveiling children's theory of mind with resting state fMRI. And this is our presentation outline. In this project, we mainly focus on the ability of theory of mind. And theory of mind refers to the ability to understand people's mental state and use them to predict people's behaviors. And this ability plays a crucial role in social interactions, communication, and cognitive development. And for example, if you broke your mom's favorite vase and she told you, you really did a great job, you know this is not a compliment. Instead, your mom may be in a rage and you might be punished later. And as this example shows, people can use the theory of mind to infer meaning beyond literal expressions and understand the underlying intentions and beliefs. Since we know the development of TLM is a gradual progress as children grow up, we are interested in examining the underlying neural mechanism that supports successful TLM ability in children. And previous studies show people with higher TLM ability exhibit stronger functional connectivity than those with lower TLM ability. And this finding indicates that the strength of functional connectivity was modulated by the degree of TLM. And if this hypothesis is true, we might be able to use children's functional connectivity signature to predict their TLM ability. Thus, our project goal is to make use of machine learning techniques we learned in BrainHack School to predict children's TLM based on their resting state functional connectivity. And we use the Python package matplotlib for data visualization, NeLearn and scikit-learn for constructing machine learning algorithms. And all of the programming was done using VS Code and Google Colab.
Okay, so we selected a pre-processed resting state fMRI dataset from NeLearn to conduct our project. This RSfMRI dataset comes from a study focusing on investigating the development of functionally specialized social brain regions. and the participants watched a short film while undergoing fMRI in the study. All children completed a custom-made explicit TOM task to measure their TOM ability. And in our project, we mainly focused on the relationship between children's TOM scores and the functional connectivity of the brain regions. And this is the participants' data. You can see the number, age mean, and age range, and also the TOM means and TOM scores range. So, and this is the distribution of the TOM scores in our data set. We then we assign the participants into 4 groups based on their TOM scores. Then these are the numbers of subjects in each group. And then we allocated 70% of our data for training the model, while 30% for validating its generalization. Specifically, we keep the portion of participants in each group matched between the train and test subset. In that way, we can increase our model validity and avoid the case that we only build our model with high TOM participants, but use it to predict those with low TOM. And we established the machine learning model with the training subset, and the table shows the evaluation of our model. Then we use those unseen data to validate our model. This plot shows the relationship between the predicted and real TOM scores. And this is the plot, shows the coefficient of each brain connectome. Okay, so we then transform this feature importance plot to Lee's brain connector matrix so that we can more clearly see the weights of each brain region connection. And we plot all the weights to the brain map, but this is kind of hard to interpret the meaning. So we set the threshold to 0.009 so we can observe the more important connections. And the connectivity observed in the brain, particularly with the OFC region, appears to have a significant impact on children's theory of mind ability. Okay, although our results is kind of inspiring, but there are still some limitations. So in the future, we think we can transform the TOM score to better fit into the linear model, because right now the TOM score is negatively skewed. And second, we can utilize bilateral atlas to capture the association between the 2 hemispheres and TOM ability. And maybe we can try more other machine learning algorithms to confirm our present results. Lastly, maybe we can focus on primary ROIs, such as the prefrontal cortex and insula, to gain deeper insights into the association between functional connectivity and TOM ability. So in this exploratory project, we observed the pivotal role of OFC connections in predicting TOM ability. This finding is intriguing as we did not set any ROIs in our machine learning analysis. Yet, our results are consistent with previous research suggesting the importance of the OFC or VMPFC in TOM ability. However, this is only a preliminary project, and we still need to try other machine learning algorithms and more data to develop a more robust model to predict the TOM ability with functional connectivity. Okay, so before we finish our presentation, we are grateful for all the organizers, instructors, TAs, and fellow participants to hold this amazing BrainHack School. And we especially want to thank our instructor, Charlene Lee, and our TA, Ingrid Zhang, for their inspiring work and assistance with our project. So thank you all for your attention.
Hey, thank you for the presentation. And yeah, the result is very fascinating. Yeah. particularly while adjusting the threshold, the frontal ROI just pop out as the most contributed region to predict TOM ability. Yeah, that's pretty cool. Okay. Okay. So I think because the constraint of time, so if anyone have the question about the presenter, please just post your message to Discord, or you can just put a message in the chat so the presenter can look at it and then maybe later talk to you privately. Okay. Okay. So let's move to yeah. Thank you for the presenter again. Okay. And so then let's move to the next presenter. So then Ting-Hsin, you can start to share your screen. Okay.
Can anyone hear me?
Yes.
Okay. So my project is to use N-gram model, surprisal that is calculated by N-gram model to match with the brain data so that we could understand how English as second language learners to comprehend English speech. So before I dive into my current progress, I wanted to give a bit introduction about the tools and also the analysis that I was using. So first of all is the N-gram model, which is not exactly or not a normal N-gram model is to use the words, the actual words to calculate the probability of the next word. But the N-gram model that I'm using right now is actually the POS, which is the part of speech of that particular target word, so that we could understand whether every connected word and its represented part of speech is comprehended by the English as ESL's learners. So that is the short introduction of the N-gram. And also, but before we match with the N-gram calculated N-gram values to the brain data, we need to switch to a value called surprisal, which is actually a bit similar like the N-gram value that we calculated, which is to calculate the target word or the probability of the target word occurrence based on the previous linguistic context. And now we use the trigram, which is to collect 3 words per unit so that we could calculate the target words based on the previous 2 words. And as for the data analysis is the temporal response function, which is a bit similar to, or it's not a bit similar, it's a bit entirely different to the traditional ERP analysis. Temporal response function is a convolution model so that we could fit into the predictors that we produce, for example, the N-gram value or the surprisal value that we produce, so that we match with the predictor, and also to fit in the EG data or the MEG data or the brain data into the model, so that the convolution model would calculate the TRF function that represent the predictor. So, and then we use the cross-validation to get the predictive power so that we could understand the at what time or at what region of the brain will respond to the predictor. So that's the brief introduction of my tools. So the current project, I would say, is not complete because due to some lack of components that I didn't notice at first. So now to do my project, I need to have a parsed text and also POS tag material so that I could calculate the surprise and also the POS frequency. So things I've done is to feed to put all my stimuli that was listened by the participant previously into this POS taggers. And it's a free online tagger, so it costs a bit time and also some energy. So I have to copy and paste every single stimuli that listened to by the participant onto the website. And then I have to do and also after the POS taggings are downloaded, or I copy and paste it and download it, and to do some pre-processing to exclude some space and error or unnecessary things. I could give you a brief view on the parsed POS. So it will produce something like this, or sorry, let me see the raw POS tag. We will actually saw this is the things that I copy and paste download from the POS taggers, and then I have to do the pre-processing so that it will look like this. And the number I actually cannot understand before what it represents, but I could understand that it's represent the words and also the POS tagging that they possessed. And after that, we need to use the COCA corpus, which our lab has the COCA, the entire COCA corpus, so that I could train the n-gram model or trigram model from it. And then you calculate by this algorithm. Yeah, by this algorithm to get the surprisal, which is you could see from the results will be looked like this. This is based on every n-gram model that is calculated, and you can see there's a lot of zero because I didn't use the entire corpus, because once I was trying to calculate the entire corpus, it takes longer than I thought. So the simple grasp of the concept will be similar like this. Let me give you. Once we get the n-gram model, which is it parsed into units per 3 words, and then we'll get the value of the probability, and then we'll calculate through this algorithm into the value, which is the surprisal value that you saw. And after that, I need to match this value with the image data, but also image data, I already done some pre-processing, which is go through the denoise for the image data that collected from the Academia Sinica, and also some ICA to review heartbeat and also eye movements. But in order to go to the final stage of the TRS analysis, there's one key component that I have to calculate, but I don't have right now, which is the word onset time. So the reason why I haven't done thoroughly to the full analysis is because I lack of this key component, because that it's something that would require to do the TRF analysis. So, but I do already have another set of data that already done through the same procedure, which, so I will give you the this slide so that you could see, get a simple concept, the grasp concept of it, how the data analysis will present it after I've done the whole thing. And so that this is the 2 data sets that I've already have. The native data set will be the open data set from the researchers that I didn't introduce before, but yeah, which is from the Brain and Health. Yeah, the Brain and Health. They've done research that conducts the research they conduct in 2019, which is to let the participant passively to listen to the first chapter of Alice in the Wonderland, and they collect the whole each data, so that participants don't have to do anything during the experiment. They just only have to listen and answer a simple comprehension question after the story listening. And then after, so the result, I used the data from the open data sets, and then I get the results from, which is represented by the engram TRF, will be similar like this. And also I've, from my side, I've collected another group of English as second language learners in Taiwan, and they all do the same procedure as the natives and calculate it and do data analysis as natives. Then you can see there's an entirely different response compared to two participants. So that, but this is the analysis. Yeah. So that will be the end of my presentation. So there's some future work that I have to do, but yeah, the final result will be similar like this. Yes.
Okay. Yeah. Thank you. Thank you for your presentation. Yeah. And also, Amanda has a question about the procedure of getting the POS tag from the website. So, yeah. So if the website has some API interface you can access, maybe the POS tag can be done
to answer that.
using, yeah. But yeah. So probably you can look into the resource of the websites if they have some like information about how to get the POS information with something like API or something else. If that exists, then it will help you to do that faster. Yeah.
Well,
Yeah.
the quick question will be no, they didn't
Ah,
provide any
okay.
source code online. So that
Okay.
the reason I have to do it all copy
Okay.
and paste, because they require fee for that. So
Okay.
if you need it,
Okay.
yeah. So
Good.
and also they limit the input time, like, or like they limit the time.
Okay.
Yeah. So you
Like you have to
don't-
purchase a license to use
Yeah.
the API. Okay.
Yes.
Okay. Yeah.
And
Thank you for the update. Okay. Yeah. So now let's move on to the next presenter. So Ruo-Chi, and can you start to share your screen?
Yes, can you hear me?
Yes. Okay.
Okay.
Okay. Then please share your screen.
Okay.
Okay.
Good afternoon, everyone. I'm Ruo-Chi Yao from Taiwan Hub. My subject topic is the effects of word frequency, orthographic neighborhood, and part of speech in word processing. It's a image study. And first of all, I would like to talk. Talk about the introduction. The word processing is influenced by different attributes of words, which can be observed via brain imaging techniques such as MEG. And in this project, I would like to focus on attributes of words, including word frequency, orthographic neighborhood, and part of speech. Okay. And I'm sorry, something wrong with my. Okay. In word processing, high-frequency words are handled more easily and quickly than low-frequency words, and orthographic neighborhood refers to words that are similar to target words by differing in only one letter, And as for part of speech refers to the grammatical category or class that a word belongs to. And as we all know that all definition for this attribute from the lecture or textbook, but now I would like to find out the evidence by myself. So the project, the aim of the project is to investigate the influences of the word frequency of orthographic, neighborhood, and part of speech in word processing by using open source. As for the method, I used the data set down from the auditory single word recognition in MEG, and there are 18 subjects, but only 12 of them can be downloaded successfully. And there are 1,000 tries for each subject, which means each subject listen to 1,000 words. And there are 97 extra words specifically for semantic prep tasks that involving go-no-go trials. And all data are recorded using MEG. As for the data processing, I processed the data by using MNE Python in Colab. And what I do first I read and download the raw data, and I do a filter and downsample. And I find event ID and read information from Excel files by using metadata. And then I do artifact rejection and slice the data into epochs. And finally, I worked with the epoch metadata and visualize evoke data. And I can show the Colab. So what I did is I download the raw data and I try to read raw data and load data for 12 subjects. And I try to load the Excel. There are lots of information about the trials. So I use the metadata to download the information, and then I do artifact rejection and slide to epoch. And I also do the average. I can find some plot. And then I work with the epoch, like I try to figure out the frequency. So I divide to two categories, high frequency and low frequency, and I can plot the data. Then I can pick one to find out the result. And so I do 3 attributes of words, frequency, word frequency, and the part of speech. Here I just see the noun and verb, 2 categories here. And last one is it's a orthographic neighborhood. I also divide into 2 categories, low and high, and I can find the inference of the author for the orthographic neighborhood here. So I do 12 all the subjects. And so I pick up some information for the first one. The result frequency effects, I can find the evidence for the frequency effects here, and also I can find some difference in some subjects. So I can see that the difference between a low and high orthographic neighborhood. And finally, as for the part of speech, I look at the nouns and the verbs. So I also can find the differences between nouns and verb in word processing here. Yeah, and that's all for my presentation. Thank you.
Okay. Okay. Yeah. Thank you. Thank you for your presentation. Okay. Yeah. So yeah, I can add some comment about Ruo-Chi's project. So doing this kind of data analysis with a single trial image, sometimes we want to have different way to pick up another set of data to do the averaging. But so now MA Python has already allow you to incorporate like some Excel spreadsheet. So it contains like item by item information, but you have to sort the you have to sort the columns so to make the number of items match with the sequence of the stimulus for each participant. Then that information can be merged into the epoch object. Then you can just select like I want to have averaging with low frequency word, and the category should be like a verb, and the number of neighborhoods should be like within one range. So now it will allow you to do this kind of well, user-defined way to get averaging data waveform. So this is part of what is, I think it's very cool. Like for people we interested in like decision making, like in a gambling task, you can have the history of a trial. Like this trial is followed by an incorrect trials, or this trial is like the third trial after losing amount of money. Then you can using this kind of annotation in the metadata. Then you can have like an average waveform for like having the feedback related activity, or like monetary losing activity, something like that. Okay.
Thank you.
Yeah. So yeah, I think we still have 1 minute break now. So based on the schedule, I hope we can still stick with the schedule. So let's have 1 minute break. Then we will be back in 1 minute. Okay. Okay.